Okay, so welcome everyone to the afternoon session. So we'll have Riccardo and Veronica talking about machine learning and applications to physics, and in particular to string theory. So Riccardo will start off, and then we'll have Veronica in the second half. So thank you.
Okay. So first of all, thank you for the opportunity to be here. As you've seen, the idea is to show some application of modern techniques in automatic learning to string theory, but more generically to theoretical physics. So I will start off by giving some motivations on why automatic learning, why machine learning in theoretical physics, and why specifically string theory. Then the main idea is to provide some introductory course to neural networks, just to have everyone a basis on what we usually do when we talk about machine learning on string theory. And why particularly neural networks? Well, in general, neural networks to public or physicists are quite natural because the mathematics behind it is not very difficult, and it also allows the speaker, or basically it enables the possibility to show the versatility and the versatility of modern developments. And finally, maybe I will propose something a bit different from the first talks. So instead of dedicating an entire session for discussion on Q&A, let's take the entire hour and a half for discussion. So please, if you have comments, questions, or suggestions, or even additions, please come forward. So let me start by some motivations on why we want to do this. So, well, basically, that we usually have in physics. And the idea behind automatic learning is basically to trade this approach, which is usually very complicated, with a more feasible, let's say, optimization problem. By more feasible, I would say something which is definitely doable. That doesn't mean it's easier, but at least it's doable. And in return, we would like to get some insights, possibly, on the physics behind the particular process that we are talking about. So one thing we can start to see, for example, is what and I will try to be consistent with abbreviations, so please stop me if not. So we can start by seeing what can machine learning do for physics. Well, let me start by one example. Well, we know that in string theory, we have a huge problem. Namely, we have a 10-dimensional theory. We want to reduce it four-dimensional effective field theory, so we need to hide 6 dimensions somewhere. And here we find the very first problem, because basically the number of possibilities in which we can do that, it's huge. It defines the string landscape, and even if we go beyond it and we start to talk about the swampland, well, it becomes infeasible to address. And for example, just to give you an idea, if we count the F-theory compactifications, in 2015, the number of possible compactification was estimated to be a power of 10, which I will not even try to pronounce. But if we were to brute force tackle this problem and going one by one, all the possible models. And if we take 1,000th of a second for each model, that would still take more than the lifetime of the universe. So of course, this is not possible. The second question that we can ask is also how difficult are problems related to compactifications. And well, if you try to address common problems in compactification, you find that most of the issues that you find are of class NP, and in particular, they can be NP complete or NP hard, and in some cases, even undecidable. So it could be very, very hard to devise or to write an algorithm which consistently takes into account all possible models. And this is a result which is not new, and it was more recently revised by Jim Halverson and Fabian Ruller. Finally, another question that we may ask is there something else? So can we do better? Can we use non-deterministic searches? Can we use something automatic which allows us to explore or even to get a direction in which we should look analytically? So what about, yeah. So the difference between NP complete and NP hard in this moment, I don't remember. An NP problem is something that you can compute in polynomial time. You cannot compute in polynomial time, and you cannot check in polynomial time. So basically, it would take a huge amount of time to check that the answer is actually correct. Exactly. Undecidable, it means you really do not know. Usually, it's a worst case. It's a worst case scenario. Oh. Thank you, by the way. So coming back to automatic and non-deterministic searches, what about them? Well, here I may try to give you just a bit of bibliography, because there have been many attempts at exploring this. So basically we start off by the very first paper, to my knowledge, that introduced an algorithm for exploration of the landscape in string theory using genetic algorithms. So this was the very first. And the two authors, Abel and Rizos, basically understood that this kind of automatic searches may be the only possibility that we have to explore the landscape. Then we have other attempts at computing Calabi-Yau metrics, for example, and topological scalars starting for Calabi-Yaus. So if you're interested in this kind of computation, and more in general, if you're interested in a review, there's a very good review which probably is the state of the art, actually, in data science for string theory. Unfortunately, this is not on the archive, but it is on Physics Report by Fabian Ruhle. It's very complete, and it's very well written. Another problem that we may face, another example that I may give you, is something more mathematically oriented or with some application to string theory. So, for example, you may want to address the problem of computing topological invariants. So you basically have a certain topological space. I will not hide from you, we are talking about Calabi-Yau, for example, and you want to output topological invariants that have some links, for example, to 4D effective field theories. And for those of you who know what I'm talking about, for example, if you want to compute the Hodge numbers, which are the complex dimension of the cohomology of a certain manifold X, where X is a Calabi-Yau. And this was, for example, tackled with some success more recently using more advanced or, yeah, I would say more advanced machine learning methods, if you're interested. And finally, for example, another interesting application is something that I personally find quite intriguing, and it is something related to, for example, symmetry detection. So, what I mean by that? Suppose that you have a function from the same set, and you have another function which maps into another set. So you ask, can I detect all the points such that so suppose that you have, for example, a potential, and you are basically asking all the points on a lower dimensional manifold which basically satisfy certain identities. And this you can do, and for example, one way people did in 2020 was basically to use machine learning, to enhance the number of dimensions of the original space. And in this higher dimensional space, basically they saw that they were forming clusters of points, and those clusters were corresponding to symmetric points according to a certain symmetry. Yeah, of course.
The third point, what is the application in string phenomenology of the third point?
The application of?
The string phenomenology application of the third point. I just missed.
It's more related to theoretical physics. That doesn't mean that it has a phenomenological problem to string theory. Yeah, but
unfortunately, okay. Okay, I see. Symmetries in superpotential. Okay, good. And the related question is about number 2.2. Well, typically in string phenomenology, you want to know the chiral spectrum, let's say. So do you apply these techniques to understand also how are the bundle cohomology groups?
Yes, so there have been research on that.
Okay, good. So it's not just standard cohomology, but also the I see. Okay. Thank you.
And opposite to what we saw right now, so we can also ask, what does physics do for machine learning? And this is something developed very, very recently, I would say. And it basically provides, in some sense, an explanation and behavioral analysis of how machine learning and how, for example, neural network work. And one example is, for example, I don't know if you ever heard of the neural network QFT duality. And this is you basically, if you are interested in this, you basically want to see most of the works by Jim Halverson and collaborators, starting from the very first. The very first article. And the basic idea here is the fact that suppose that you have a function which is parameterized by a some parameters theta, and which is defined by a single scalar hyperparameter. I will define it later, but the idea is this number should give you the size of your algorithm, which may as well be a neural network, which maps from a certain d-dimensional space to another d-dimensional space. And the idea is that in the large n limit, the distribution function of your neural network is a Gaussian process. And by Gaussian process, I mean you can basically see the problem as a free scalar theory. Because in this case, the Gaussian process, the action of the Gaussian process is defined by x so you see that you define this as the covariance of the outputs, and you see that you can basically study the correlation between the outputs of neural networks using standard arguments in quantum field theory, because you can compute the k-points correlation function through the path integral formulation using the Gaussian process. Clearly, this is not the end of it, because this limit is both unphysical and numerically unachievable. So what you may want to ask, for example, what's the finite n limit? You can basically see this as a correction to the Gaussian process. And in this case, the delta S, so the additional parameter that you add, are interactions between the outputs of a neural network. So you can basically, again, use standard quantum field theory to basically study the correlation of the outputs of the neural networks.
Sorry, can I just try to understand this a little bit better? What is X in this case? I mean, I understand the free theory and the QFT interpretation, but what is X?
X in this case would simply be your inputs, the inputs of the neural network, and f of x is the outputs of the neural network.
Okay, thank you.
And while we're at it, we can also go beyond this. The duality is, I would say, it's perfect the way it's defined in the large n limits. That's a good question. Nobody has a right to that. I don't know. So the answer is I don't know if there's a lattice connection to this. Also because there are some problems connected to the definition of the propagator, so the inverse of the covariance matrix. Because differently from quantum field theory, in this case, the propagator highly depends on the choice of the neural networks, on the type of the neural network. So it basically depends on the activation function of the neural network. And that choice, in some cases, may impede the study. In some other cases, it may render it more easier. So that really depends, and there's not yet, to my knowledge, a formulation on the lattice. Another continuation from that, since you can define in the finite n limits, you can define this as interaction depending on certain coupling constants. Of course, you can try to study this using the renormalization group. And this is something which has been done recently by a group in Paris. They showed how to tackle the intrication and the correlation of the outputs of the neural network based on non-perturbative approaches to the renormalization group, basically based on the Wetterich equations. And just to give you an idea of how interdisciplinary is this kind of approach, in the collaboration that first put out this, you have a string field theorist, a mathematician, and a permanent AI researcher in Paris. So this is basically becoming a strict collaboration between the AI community, the mathematics community, and the theoretical physics community. Finally, in the more motivational parts, there are also interesting application for those of you who are more interested in having analytical results rather than numerical results. So let's call this machine learning for analytical methods. And for example, you have quite a few works in the literature which basically took machine learning as an input, and by studying the results of the machine learning, they were able to prove conjectures, prove theorems, and so forth. So, for example, a first example, the inputs of the machine learning part of the research are reflexive polytopes, the outputs the possible toric threefolds that you can construct from polytopes. The machine learning was able to give a conjecture, the number on the occurring of E6 compactifications, and it was later proved by the same group using analytical methods. Please be gentle, that doesn't mean I know perfectly how they did it and what the objects are, but another example took as an input, again, reflexive polytopes, in this time in 4 dimensions. And the output is the number of possible triangulations of the reflexive polytopes. And basically, the machine learning gave an estimate on the number of triangulations. And it was later proved by the same group there are also other possibilities. So, for example, another group was able to prove some analytic rules on F-theory compactifications. And for this, if you're interested, is in a more paper. And something which is interesting also on the computer science side is a work by Herbin and Krippendorf in 2018. They basically used machine learning to generate superpotential starting from known superpotentials. So you basically use machine learning to input possible consistent superpotentials, and the idea is to use machine learning to generate new consistent superpotential of which you do not have knowledge at the beginning, as an idea to explore possibilities in supersymmetry. Where? The number of compactifications in which the exceptional group E6 is appearing. To be honest, not. Of reflexive polytopes. To be honest, I'm not really sure.
Okay. I was just wondering what is the application in string theory of this?
Again, not necessarily string theory, so as a matter of fact, I guess that Veronica will may also comment on that later, okay. But applications strictly to string theory of machine learning, not so many. Okay. It's more general on algebraic geometry and with possible applications to string theory. So sometimes the applications are purely mathematics.
I misunderstood. I thought the word compactification meant something in string theory. No.
Okay. So let me just add, I think that was the first paper where some pattern was detected. There was a conjecture, and then that was proved analytically.
Exactly.
I think the relevance of that paper is through this process. Okay, it's algebraic geometry, doesn't necessarily go into compactification.
Yeah. Okay. So this should conclude the parts or the motivational part. So if you have comments or other, please do not hesitate. The idea is now to tackle directly the definition of probably the most used and the most important algorithm that we have in machine learning. And as I told you, probably it's not really the first that comes to mind, but for a public of physicists, definitely it is the most appealing. So we are going to talk directly about neural networks. And the idea is to first show some building blocks that we have to build the neural networks, and we will later see some applications. So the very first building block is the so-called perceptron, which is at the basis of all neural networks, of all what we know as fully connected neural networks. The perceptron was first conceived by Rosenblatt, and it may be a bit astonishing, but the first result is not new. So it's something that came in 1958 at the Cornell Aeronautical Lab. And the very first idea to use the perceptron was to do some pattern recognition. And even more interesting, at least for me, is the fact that the very first implementation of the perceptron was hardware. So basically based on logic gates and on calculators that probably would take the entire room. So this is because the software implementation came really way later. And the purpose of the Perceptron is to provide a linear classification by mimicking the behavior of the human brain. This is just, this is really just the idea behind it, but as you can see, the implementation is also quite simple, because the basic idea is to take a certain input, multiply it by what we call a weight, add a bias, and produce an output. So this is the basic idea at the heart of the Perceptron, as it was devised in 1958. In formula, as we would probably write it today, we take xi to be a p-dimensional vector, where I goes from 1 to n. Our input is a matrix whose rows are the realizations of the vectors. So this is n times p. The notation, maybe it's not really what you are used to, but in general, in computer science, this is a standard notation for matrices. And the output of the Perceptron is simply where the bold 1 is simply a vector, an n-dimensional vector with 1 over all lines. And the visualization, which will come useful in a moment, is basically that of a vector which is fully connected to the output with weights. This is P and the bias. So this is the very first visualization of the Perceptron, and may I point out the fact that this is a linear application, and this is a huge problem, because basically the only classification, the only functions that you can approximate using a Perceptron are linear functions. And historically, that led to abandon neural network research for basically 20 years. And to see it...
Sorry, can I ask a question?
Yes.
Why, in what sense is this different from a linear fit? From a linear regression, you would do and call it just a linear regression?
The Perceptron, in a sense, is a linear regression. It's a hardware implementation of a linear regression. And so at this stage, there's literally no difference with a linear regression.
And what's the role of the bias? Is just to have an extra degree of freedom to
Exactly.
fit?
Yes,
okay.
It's the intercept of your best fit. And in fact, people in 1958 very quickly realized that you may have a problem. So for example, if you want to provide a classification of a very simple function of an OR gate, this you can do very easily, because basically this is linear. You can provide a linear classification of this. A Perceptron would be able to trace a line and to distinguish the true from the false classification. But, for example, you can immediately add some difficulty to the perception by modeling an XOR gate. And the XOR gate very similar, but it is exclusive. And you can see that there is no way in 2 dimensions. This is linearly separable. Because you cannot trace a line that completely separates the empty dots from the full dots in 2 dimensions. Of course, if you go in 3 dimensions, you can elevate 2 and use a plane. Okay. So we are basically missing some elements inside the perceptron, or if you want, inside linear regression. This is why people first introduced the idea of the perceptron, and then fully neural networks, which are at the heart of many implementations use. The perceptron is a function made of a collection of weights and biases labeled by a certain parameter L, which is a certain set, order set of labels, and which takes a certain input. The idea, visually, is to take the inputs and connect it to intermediate representations. So, for example, you may have one here. Sorry. And then y. You still have one problem, though, because if you see it in formula, in which, one thing. It's very common to reabsorb the bias factor inside the input vector. You just need to add one entry inside the vector. So for the moment, please let me avoid the addition of the bias factor. And in this case, the weights are matrix which basically the input at the layer L-1 and basically output the layer L. Sorry? Yeah. Z is an intermediate representation. So the idea of the multi-layer perceptron is really to create a net. I didn't want to use network as a word. You have to create intermediate representations that you use again and again in order to arrive to the output. In a sense, you perform multilinear regression on the input, then you perform multilinear regression on a second layer, then on a third layer, and then you arrive with. You can reduce it, you can enhance it. It depends on the possible application. However, if you put it in formula, you very quickly realize that you still have a problem because the output is simply your input times the first weight multiplied by a second weight and so on and so forth. You simply redefine this as XW and you again have a linear separation. So you are missing another element. And the element which defines a fully connected neural network is a multi-layer perceptron which is made of weights biases, and activation functions, which have a very specific role and very important role in neural networks. So this is the definition of fully connected neural networks. And let me define it a bit better. The idea of a fully connected neural network is basically to use the activations functions to provide a layer of nonlinearity in your regression. So the idea is to compute an intermediate representation of this kind, where A of L is a function applied on ZL. And A of 0 is simply your input. This is indeed a fully connected network, because basically what you're doing is you take your input, you first compute an intermediate representation, Z of 1. You then add an activation, you continue, and you get to your output. And the necessary condition for the fully connected network to provide some nonlinearity in this case is, first, it has to be nonlinear. So f of L has to be nonlinear. And second, you will see it later, it has to be differentiable. And if I'm not mistaken, it has to be at least class C1 on the domain of definition in order to be computable. So, or activation functions are commonly used in most applications. In most applications, I mean, for example, in image recognitions on things that we carry on our phones or laptops. And the very first example is what is known as rectified linear unit, which has a very simple definition. And whose representation is very simply this. I know you can immediately tell me that in 0 this is not differentiable, not for a computer scientist, I would say, or for an engineer. So let's accept the fact that in 0 there are no problems, at least numerically. And for a modern application of the I will give you the bibliography. That using these activation functions not only provides the best results, in particular case for image recognition, image classifications, but it also provides a way to speed up calculations by a very large factor. Option, second choice, is something very similar, which is called leaky ReLU, or Z. Depends on a certain parameter alpha, and the definition is extremely similar. It basically provides a way to let some negative number to leak out of the activation. So if you basically the ReLU function will kill all the entries of your layers which are negatives. If you do not want this kind of behavior, you may try to use the leaky ReLU function. A third example, very, very common, is the hyperbolic tangent. And I don't have to show much about this, but the basic idea is the fact that since this function is constrained between -1 and 1, it may help numerically to avoid exploding your activations. I don't remember, okay. Finally,
sorry, one question. What principles should I use to choose between one of these, and how sensible or how sensitive the results or the computing time would be on the choice of the activation function?
Unfortunately, most of the guiding principles are trial and error. So
okay.
You put this into what you call the optimizations of your parameters. So you try ReLU, you try ReLU, you try hyperbolic tangent and see what gives the best result.
I mean, but the constraints are this 1 and 2, nonlinear and differentiable. So there's a huge space of possibilities. What
yes.
other
But there are also some other guiding principles. So for example, suppose that you want a model which scales with the input. So you are basically you will not use a hyperbolic tangent. You may try to use ReLU, it will not work. You may, for example, try to use a square function if you want something. So it mostly depends on what you want the neural network to learn. So for example, if you want something which approximates a homogeneous function, homogeneous function, then you may have to use homogeneous activation functions. If you want something which doesn't explode, you may want to try the hyperbolic tangent. If you see that you have problems with exploding activations, you may try activation functions. And for example, in this case is very used in what are known as autoencoders. So if you want an autoencoder is something which I may even try to show you later with the Jupyter Notebook. If you have an image as input and you want to reconstruct the same image as output, there may be cases in which you want to do this. Hyperbolic tangent has proved to be effective to lose less information in the process. Other examples of activation functions, the two examples that I'm going to give you are usually activation functions that you can use also inside your networks. I don't know if I made it clear, but the activation function may change layer from layer. So you're not using one activation function for all the network unless you need it. And these are activation functions that you may, for example, use as the last layer, as the last activation. And one is the sigmoid function. One over 1 plus e to the minus z. Sorry. This one. This 1/2. And why in particular? Because this is constrained between 0 and 1, and it's very useful to recreate probabilities. So suppose you want to classify something, you want to have a probability as a return, you usually use the sigmoid function. And the reason is simply, suppose that you have a certain probability for, and you construct the logarithm of the odds of success. This is known as the logit function. Exactly the inverse function of the sigmoid. So this is why basically we use this. We use the sigmoid to model a probability in a neural network. As an extension to, and this is super important in machine learning, is the softmax activation. The softmax activation is actually a generalization of the sigmoid because it is the x one of the layers by k z 1k. Okay, so this is the definition, but you may ask why in this case z is a matrix, or at least why it has two indices. And the reason is that the sigmoid is very useful to model the probabilities of something which is either class 0 or class 1. So if you have only two classes. And by this, I mean one class classification. Your output is either 0 or 1. But if you have a multi-class classification, your output is something more general and may assume different values. To model this in machine learning or even for a neural network, what you usually do is you introduce another kind of output which has two indices, and this is equal to 1 if okay, or 0 otherwise. And very simply, this basically shows you that if you have an input which is something like 0, 3, and 1, you transform this into a matrix which has 1 only when the first component is equal to the class. In this case, like this. In this case, like this. And in this case, you can use the softmax activation function. Yep.
Incredibly basic questions that I'm a bit struggling understanding. So far, I mean, it looks to me that you are just modeling some functions of some inputs. Let's say you have some x, and then you have some something that is just you multiply the x by something, yes, or you do operation, and so you generate classes of functions of x.
Exactly.
But I'm not understanding, like, there are all these parameters, and then what's about them? What's the rule of the game? What do you do with them?
Can you give me 2 minutes?
No, okay. So
I'm going to get it, because actually you are introducing the next step. So basically, up to now, what we can do is basically compute what is known as the forward pass. The forward pass is basically going left to right in that schema. Okay. So you basically take x and you model a function on it, and you get the output y that you want to approximate. So not unlikely normal linear regression. The problem is what is learning and what do I learn when I say machine learning or deep learning. And the idea is to give the machine something to learn. And these are usually referred to as loss functions. very basically, a neural network is made of 3 elements: the forward pass, the loss function, and backpropagation. So now this is the second. Yeah.
When you add the function f, the activation function, right?
Yeah.
How can you be sure that something converges to your algorithm? So you have something starting from your input, so you want an output, right?
Yeah.
How can you be sure that something converges to some output, and it depends clearly on f,
so
right?
That problem is partially encoded in the choice of the f,
yes.
But this is left to optimization, so you have to try different versions. And the second is encoded in the loss function. So it is the loss function that tells you if something will converge or not.
So I really have to, find out the right f to have the right convergence. That's the...
Yeah.
Okay.
In general, yes, and you have to try different choices, different combinations.
Okay, thank you.
There are some guiding principles, but I've talked to many AI researchers, and the answer was always the same. It's experience that tells you which kind of activation function you use at the end. So for the moment, I trust them. I had no choice. So the idea of a loss function is how do I guide the neural network to learn something? Case 1, you do not know the answer. So basically, you take what I told you up to now, you take out y from the scheme, and you are basically left with something which is very, very tricky for neural networks. In fact, neural networks are not really for this kind of problems, but nonetheless, something can be done. But this is the domain learning. So you are basically doing a genuine exploration of your input. You are basically transforming your input in some other representation, which hopefully will help you to get something in return. So for example, suppose that you have an input which forms some very nice clusters of points in your 2D plane, or even in your d-dimensional space. You may try to use unsupervised learning to actually find out the clusters that you are forming. This is called, with a lot of fantasy, this is called clustering, which we have a lot of variations. But for example, you can also have a signal hidden in a lot of noise inside your let's say in a spectrum. You want to take out the signal and to analyze it, you may try to use what is known as principal components analysis, which basically tries to recover the direction in which the signal is stronger. These are, however, not based on neural networks. For neural networks, you can do something which is known as contrastive learning, which is something which is developed a lot by Google at this moment. And the basic idea is take some objects. Suppose that you have 4 objects. 2 of them are equal, and 1 of them is of another kind. You basically use a neural network to output a new representation of your objects, which in principle is different. And you basically tell your network to learn to attract the 2 representations of the same object and to repel the other representation. This way, you are basically trying to let the machine learn how to move points on a plane, and you're basically telling the machine to make 2 points converge, and 1 point to be as far as possible in order to have, for example, to very well distinct clusters of points. And this is something that you can find on the archive by Google and Stanford Research, I would say, the department at the Stanford University for AI.
So now you talked about the perceptron and then the multi-layered perceptron, which is the fundamental element of the neural network, right?
Yep.
Okay. And then the neural network will be a collection of these
building blocks, elements. Yeah.
okay, interacting in some way.
Yeah.
Like, okay. But more, I mean, how will they interact? Like
I will show it explicitly in the case of supervised learning and not unsupervised, because otherwise this would take a lot of time, and also this is not very well defined. It takes,
okay.
This is an open research problem, in fact. Unsupervised learning for neural networks is really difficult, I would say.
Thanks.
Second case.
Sorry, another question.
Yep.
You were saying some points were closer or farther, like, but what is the space? What is the distance? How do you define that?
Okay, so in this case, you would train the neural network to output, let's say that you start from p-dimensional vectors. You would ask your neural network to output p-prime dimensional vectors, and you would use this representation to operate with the neural network. So in order to train your neural network to recognize when two vectors are similar or when two vectors should not be put together. The fact that I put it on a two-dimensional plane, it's a simplification.
Okay,
of
but
course,
it's just a distance in RP. It's just that.
It's
usual.
very general.
Okay.
So if you're Google, this is a 2048 dimensional plane. So of course you cannot do that.
Okay, thanks.
You can use another layer of unsupervised learning. You can use principal components analysis, reduce to 2 dimensions, and plot it, but it's another story.
So you have half an hour, okay?
Okay.
There was a lot of discussion in the meantime, so.
Okay. Case 2, you know the answer. And so you basically want to model a distance function from your true result and the output of your neural network parameterized by certain parameters theta. And you see this as a function of the parameters in y. So theta is the output of the neural network. The criterion that you choose to define this loss function is based on what you want to learn. And for example, one criterion is based on the likelihood function. The likelihood function models the joint probability of your outputs given certain parameters. However, this is not, when you talk about likelihood functions, this is not a probability distribution function because you see it as a function of the parameters, and this is sometimes defined this way, just to remember that the real parameters of your functions are theta, and the interpretation of the likelihood is basically the function that models the most appropriate parameters that could have given the outputs. And basically the way you choose the parameters is by saying that the optimal parameters are those parameters which maximize the likelihood function. And this is known as maximum likelihood estimate, which is at the heart of all regression and classification algorithms. So let's see specifically how this translates into some particular cases. And the very first case that I want to show is classification. So suppose that you want to model the probabilities of an output, and I was not careful enough. The fact that you define a vector which is 1 only when in the entry which is corresponding to the class is called one-hot encoding. I forgot to tell you this. And because here it is actually important because we are directly talking about outputs which are k-dimensional with an index I, which models the number of samples that you have in the set. In this case, you can model the likelihood function very simply, because it's basically the function that tells you the best observation of your probability. So theta of index y and k elevated to epsilon of y and k. And this is probably not immediate, but you basically have to see that this is a vector of 0 and 1. So basically the only surviving entry of your output is the one corresponding to the true class, to the one that you have here. Probably this way could be easier. So this is a discrete output. This is a continuous output from your network. What you actually tell the network is not exactly maximize that. The maximization procedure is could be numerically unstable. This is why you translate your maximization problem into the minimization of the negative log likelihood. Your loss functions is nothing more than the negative logarithm of your likelihood function. And your best parameters, so the parameters that the neural network should find are the parameters which minimize this function. And you can see that in the case of classification, L of theta becomes, once you also consider all the realizations in your set, this becomes the negative log likelihood, and you can see that this is minus the average over I. The product becomes a sum of this object. Which probably some of you may already recognize, because this is the expected value in the distribution of I of the log of the output of the neural network. This is known as cross entropy. And this is just one example of the possible loss functions in the classification case, but it's definitely the most used. a second case, which is different because it's about a regression problem. So in this case, you do not want to model the probability of an output, but in this case, you directly have an output which is a real number. The idea of the neural network is to model a function on the number. So in the best case scenario, what you want to model is something which approximates your output, exception made for a residual error. This residual error, you take some assumptions, and in particular, you don't want it to be dependent on the dependent variable, the x, which is in input. So you basically say that your epsilon, your residual, should be completely random, or possibly extracted from a normal distribution with zero mean, because you want to model this, and with a certain variance, sigma squared. This means that this value is Gaussian. Hence, your likelihood function becomes very simply an exponential. And I will let you, as an exercise, to show that this translates into a loss function, which is the negative log likelihood of this, which is 1 over n, sum over all possibilities of the difference of the squares. Or even better, the chi-squared function of your regression. This is also known as mean squared error, which you usually find when you are working in when you are reading papers of in machine learning.
Sometimes in physical systems, you actually have some like stochastic noise or something, which in that case, this error is like sort of like a white noise, and like in turbulence, I think you have some very like fluctuations. And what do you do? And how do you model
in that
this?
case, it's actually the interpretation means that. So if I understood correctly, what if x has some dependence on x, and then you have a problem with the model, because in this case, you have a heteroscedastic behavior, which means you have a trend in your noise given by the dependent variable, which means that your model is not complete, which is another way to say your model is kind of wrong. So it's not taking into account all the possibility, all the variables, in a sense.
And then what you do, because really it's like, if I imagine that my input is like some velocity field in my fluid, and I have really a highly turbulent fluid.
Yep.
In that case, I think somehow use some stochastic like description of the system,
yep.
like in that case. And how can I teach to this kind of machine learning thing to extract some information about some late time distribution of the velocities or something like this?
In that case, the first thing that comes to mind is do not use the mean squared error as a loss function.
Yeah, you can use, no, exactly.
In general. And the second option is, are you really certain that you cannot avoid in any case the dependence from the dependent variable for the noise? I don't know. This is... there's Veronica, which probably have...
You tend to have heteroscedasticity problems when you, if you have your standard statistical model, right? So I have a model which is rigid. For instance, I have I want to do some regression. And therefore, maybe I'm choosing the wrong variables, or maybe my model is not complete enough, for instance, right? But in this kind of setups, where more or less I can model whatever kind of function I want, is it really possible that, I mean, the error is still dependent on X? I mean, usually in this kind of models, your main problem is that you can also fit noise. So you fit too much.
Yep.
You can learn things by heart. I mean, the model, I mean, you know, right? So you think about your having linear, so point distributed on a line. If you have your linear model, of course, the error is not going to be 0. I mean, unless your points are really like that, okay? So in general, you have few parameters, but those parameters are extremely powerful because they are actually predicting. So your model is simple, but it predicts the behavior. If you do the same thing, but you use a neural network, you may end up having thousands of parameters. So your final error is going to be 0, but just because you're actually going to all the points, right? So usually, I do not think that you end up in that situation. The situation.
Exactly. I'm going to talk about it in a few minutes, but using neural networks, it's pretty tricky because of that. You risk fitting also the noise if the noise has some dependence on the dependent variable. So you are basically constructing a model with your neural network in which, let's say, how to write it, in which here you have the genuine contribution of your model plus another noise which has some dependence on X. Right. And you have to find a way to avoid that.
Right. And in case I just give just in case I really give some random numbers in that case, instead of completely random, I just use an algorithm that generates random numbers and then put it as an error. In that case, I have no dependence on X anyway.
You have no dependence, but you risk what we were talking about. So you take your data and you fit something which is totally random. Your risk that you have with a neural network is to have a model which does this, which does that, and which is of course not physical.
Thank you. Yeah, thank you. Thanks.
Just to see if I'm understanding correctly, let's take a simple example. Like the neural network is trying to understand if I have a picture of a cat or a dog. Okay.
Yeah.
So let's say it is correct.
Not in this case.
Why not?
Because this is a regression. So in this case, your neural network is really trying to learn a number.
To learn a number. Okay.
In classification, it's trying to learn if it is a cat or a dog. In the case of regression, it's really trying to compute a Hodge number starting from a configuration matrix of a complete intersection called a BL.
Okay, thanks.
I have a very basic question because I'm getting lost badly.
Sorry for that.
No, it's okay. It's just complicated stuff. Up to 15 minutes ago, it was very clear we had an algorithm that step by step was taking some input and giving some output layer by layer until the end. And now there is this loss function. I don't understand why we need it. At which point are we going to apply it? Or what is it doing for us?
Okay. It's basically, I changed the notation, so I'm sorry for that. But the Y with the hat is the output of the neural network. So you're basically computing the loss function as an additional step from your forward pass, because you are basically computing a distance from the true value. In machine learning, usually it's called the ground truth. So you basically you know the answer, and you are trying to approximate it or to model it in the case of classification using a neural network. But then you have to understand if what you're doing is good or not. So you use the loss function to see how near you are getting to the correct answer.
So at the very end, I apply the loss function, and this is feedback on how good.
Exactly. This is a feedback on how good is the neural network performing. I don't have time to show you, but of course the maximum likelihood estimate or the negative loss, log loss, the negative log likelihood minimization is powerful, but it's not enough. So loss functions are actually a bit more general. So for example, you may also define, in the case of regression, you can also define the mean absolute error, which is basically the mean distance of the absolute value of the output of the neural network. You have combinations of the two, so you have what is known as the Huber loss, which is a linear interpolation between the mean squared error and the mean absolute error. You can also try to approximate a distribution function using another distribution function, in which case you can use the Kullback-Leibler divergence. So if we want to discuss it, I'm very willing to discuss it, but unfortunately I don't have time to show it here. Yeah.
So you fix your parameters that were for this function, for this y, and then you compute the loss, and then you change the parameter if you don't like them.
And then you wait for the third, third ingredient, which I was about to introduce. And the third ingredient is called backpropagation, or as sometimes referred in the literature, simply backprop. So far, what we have is in fact what you were saying. So we have a forward pass. So basically, we know how to compute y of theta. We have the loss function. But the question is, let's say, how do I train? How do I change the parameters in order to minimize the loss function? And the idea is actually very, very basic, because if your objective is to minimize the loss function, then you can use something which is very well known to physicists. You use gradient descent. There are, let me say, there are lots of ways to train a neural network. You can use genetic algorithms or whatever. Backprop is based on gradient descent, and it is by far the best performing way to train a neural network up to date. So the idea of gradient descent, of course, you already know it, is basically to follow the direction of the gradient towards a minimum. The tricky part of the training of a neural network is, of course, to not get stuck in a local minimum, but possibly to find the global minimum of your local function, or at least a local minimum which is not the best local minimum. And the recipe to do this, it's pretty known. So gradient descent, the first step, you compute the direction of the descent or the loss function with respect to the parameters. Second step, you choose a parameter alpha positive, which you call the learning rate, and I will say something about it in a second. Third, you update the parameters of your neural network iteratively. So you have to repeat this procedure a lot of times, and you basically update it this way. The choice of the learning rate is usually very, very important, because it's basically what tells you, what makes you either bypass, either find the best minimum, or go too far and completely miss it. So the learning rate, if you want, is another very important parameter which you have to optimize in order to get a good performing algorithm. And how does this help in any way? And basically, with this definition, I'm almost done. The idea of backpropagation, the idea to compute gradient descent in a neural network is actually ingenious, easy, and very difficult to implement, to the point that this was all introduced after, let's say, more than 20 years from the, almost 30 years from the definition of neural networks, and which was even published on Nature in 1986. And the idea is as follows. You take your input, and the forward pass is pretty easy. You compute the new representation, then you compute your activation function, and you proceed. You proceed iteratively, and finally, you compute the loss function. But if you're ingenious enough, at each step, you also output another thing, which is basically the gradient of what follows with respect to what you have in input. In this case, you compute the gradient with respect to this. And as a final step, you compute the gradient of L with respect to the last layer. And you can see that at this point, if you backpropagate what you just computed, you are basically getting the derivative of the loss function with respect to the initial parameters. And this, in general, you know, because I don't want to write an idiocy, so let me check. But, well, this depends on the last activation, so let's say it's model dependent. But the derivative of the activation with respect to the new representation is simply f prime of z at a layer. The derivative of the representation with respect to x are the weights. And this you can do for each one of the layers. Last ingredient. This basically means that if for each layer you compute the forward pass at the same time you also record the partial derivation up to a certain layer, which is simply this object, L plus 1, f prime of z, L plus 1, up to, with respect, sorry, L with respect to L. Then you basically solve the problem of computing the gradient of the loss function with respect to a certain parameter. Because at this point, the derivative with respect to the weight at a certain layer are simply a chain rule with a, translated to a very, very simple formula. in a sense, you may have heard of them, but frameworks like TensorFlow, PyTorch, anything you usually use to code neural networks are simply autograd systems, which means that they do all these under the hood and without your knowledge. So they are basically computing at each layer the forward pass, this object, and this object. This object, finally, is what you use to update your weights through iterations. So this is basically what you do. This basically completes the definition of a neural network. Because basically, with this, we have all the ingredients. We have the forward path, which means we know how to calculate our results. We have the loss function, which means we know how distant the result that we calculated is from the true value. And we also have backpropagation to compute the gradient descent. And of course, the naive version of gradient descent is also numerically quite long to compute, so there is a huge number of variations of possible algorithms for gradient descent. I will give you the bibliography for the most used, which is called Adam, just because if you are interested in the machine learning for physics, basically everyone is using that. And also everyone is citing that, which means that that Maldacina's paper is not the most cited in the physics community anymore, I would say, because this is approximately 40,000 citations. So
there's a question here, and you have about 5 minutes.
Okay. I could actually stop here. What I wanted to say is really general knowledge for now. So.
Okay, just a simple question. So in this diagram you draw for the backpropagation, we are seeing the loss function as a function of the activation, and then all the way back as a function of the input. Okay. And what is the role of theta in this case?
The role of theta is encoded, well, theta is, well, let me write it like this. Theta is all weight biases.
Ah, okay. All the parameters, okay.
Yeah.
Okay.
So, yeah, the final argument is simply something for general knowledge. So gradient descent has a slight problem, or let's say is a bit tricky, because it can lead you to overfit the training set. What you usually do when you train the neural network, so this is 0.7. When you train the neural network, you basically take all your data that you have and you split it in at least 2 sets. One set, the largest, let's say, is what you use for training. And a small set is what you use for test. What you should report in a paper, in an article, is usually the results on the test set. And unfortunately, there are people who use the results on the training set as the final result, and that is not good practice in general. And the argument is very simple. Let me define just 2 things, 2 behaviors of your model, possible behaviors. Suppose you have data which are distributed like this, and you have a model which, let's say, fits them like this. It means that it is underfitting the distribution, because basically a model like this doesn't mean anything. This is a model with high variance. At the same time, the same distribution of the point and a model which does something like this. This is a model with a high bias, which means it is overfitting the training set. The classical argument for this kind of problem and gradient descent is that as a function of the complexity of the model, and here you put the error that you are doing, the training error can always be made arbitrarily small. And the reason is that there is a theorem, which is called the universal approximation theorem, and which tells you, I will give you the bibliography in a second, which basically tells you that a neural network as small as one hidden layer has the ability to approximate any continuous function. So basically, the training error is not a good metric of how the model is performing. The good metric is the test error. And the classical argument is the fact that you have the two regimes. Here, you are underfitting, so you are in a regime of high variance, in which the test error is very high. Here, you are in a regime of high bias. You are basically overfitting the training set. So the goal of the learning is to find the optimal point, which is somewhere between the two. The modern argument for this is the fact that this curve doesn't end here, and you may have what is known as the double descent curve, which, to be honest, looks more like a plateau after a while, which basically tells you that the parameters in your model that you have as a surplus are actually regularizing your fit, and you can use them to find basically a new minimum of the test error. And this is, you can find it on the archive. And this is the only place where I will actually make a comment on my behalf. And I personally believe that for physics, this is very dangerous, because basically we could end up with a model which is very, very complex. And in that case, the interpretability of your result becomes almost impossible, very, very difficult. Training is no longer democratic. So basically, who has the most powerful GPU basically wins. So there is no more competition. And also, the possibility to explain a physical model with something simple is something which is very, very appealing. So I would say that for physical problems, which are in general more geometrical, so easier with respect to industry case, we should always aim for the optimal point in the classical regime. Otherwise, we could end up like NVIDIA, the manufacturer of GPUs. 2 months ago, they came out with a paper for a language model able to do translations and to do question answering by itself with 500 billion parameters inside, just because they were able to do it. So this was just a showdown of force. So basically, they basically ended up probably here in the curve. And okay, so that's just a point to prove, in my opinion, anything at all. Also because the performance they obtained was not vastly larger or vastly greater than the predecessors. So with this, I concluded the introduction to feed-forward neural networks.
Let's thank Riccardo again. So